Hello. In this video, we are going to look at alternating series and absolute convergence. Getting close to the end of our list of series tests, but we've got a few more to get through, starting with alternating series. Now, we've got a lot of great tests in our list, in our tool belt here, but a lot of these do not work when you have negative terms. For instance, the comparison tests do not work when there's negative terms, and the integral test it has to be positive as well. So this alternating series test is going to allow us to deal with what we call alternating series. And you recognize an alternating series by noticing you're going to have a -1, or maybe it's a -2 or 3 or any number really negative to the nth power, where n is your index. And then times a bunch of other things maybe that are going on. So whenever you have that, if you start listing out the terms, they're going to alternate between positive and negative. And that is when you're dealing with an alternating series. Just make sure that it alternates every other one. You might see a series where it goes positive, negative, negative, positive. And while there's a pattern there, it's not alternating every other term. So that doesn't actually qualify as an alternating series. So keep that in mind. So what the test does is there are two conditions that we have that will allow us to prove convergence of an alternating series. And you'll notice here that it's got an, and we are using the an as the part without the alternating piece in it. So that -1 to the n is not part of the an. When you use this test, you can drop that piece out, the -1 to an n. And so one is that an plus 1 has to be less than or equal to an, or the series is decreasing. Okay, that's one requirement. The other requirement is that the limit has to approach 0. If that's not happening, then it's not going to converge. And so when you're doing the alternating series test, you're going to check both of these things. I usually start with the limit. And then if they're both true, if they're both satisfied, then you can say that the series converges. Now, something to keep in mind about condition 1 there, I will often solve this by dividing the inequality, dividing the an over, and then you end up with an plus 1 over an is less than or equal to 1. I find it easier to do it this way because you can oftentimes cancel or simplify things nicely when it's written as a ratio. So this is often the version of it that I will try and prove. And on condition 2, remember that if the limit doesn't approach 0, then that means you could do the divergence test and prove that the series diverges, because adding the alternating piece back in for the divergence test isn't going to make it go to 0 if it wasn't going before. So just keep that in mind, that if it fails that requirement or that condition, then the divergence test works here as well. Okay, so let's do an example of this one. So we're going with a really simple one here. We've got -1 to the nth over n. And so we'll start by taking the limit. And again, I don't include the -1 to the n in there. It's just going to be everything else around that. So the limit of 1 over n, well, that's 0. So the first condition is satisfied. Next, I'll do the n plus 1th term over the nth term. And so that's going to be 1 over n plus 1 divided by 1 over n. And then again, when I have two fractions that are dividing, the bottom one, I can flip and multiply by that reciprocal there. So I end up with n over n plus 1. So I have n over n plus 1. N plus 1 is always going to be bigger. So I can say that this is always going to be less than 1, which means the sequence is decreasing. Something to keep in mind here, that if this ratio of successive terms doesn't work, you can use any of the 3 methods that we learned in the sequences section for proving this. So oftentimes, if this one didn't work, I will try the first derivative and see if that is always positive or negative to prove decreasing or increasing. So you can go back to that monotone sequence section to come up with other ways of proving decreasing if this one doesn't work. Okay, so we met both of the conditions of the alternating series test, so I can say that the series converges, and I state the test that I used. And that's it. We've proven it converges. And just a note, this is a commonly used or seen series, and we often refer to it as the alternating harmonic series. And now that we've proven that it converges, whenever you see an alternating harmonic series, you can say, well, that's an alternating harmonic series, therefore it converges. Okay, next up is alternating convergent, or absolutely convergent, sorry, and conditionally convergent series. Now, this is a tricky thing to wrap your head around, so we want to really go slow through this explanation. Absolute convergence is when I take the absolute value of a series and that series converges. So if the absolute value of the series converges, then the original series we say is absolutely convergent. And just a note here that if the terms of the series are already positive, then taking the absolute value doesn't do anything or change the series. And so any series that's convergent, that's always positive, is going to be absolutely convergent as well. Now, conditionally convergent is when a series is convergent, but it is not absolutely convergent. So if I take the absolute value of the series and I get divergent, then it's not absolutely convergent, but the series could still be convergent before I took the absolute value. Now I know, kind of tricky. Okay, but we're going to do an example so we can kind of run through this a little bit. And then this theorem that kind of ties all this together. If a series is absolutely convergent, then that means it's also convergent. So if I test a series for absolute convergence and I get the result that it is absolutely convergent, I don't need to test it for convergence, the original series, before I took the absolute value, because this theorem tells me that it will definitely be convergent because it was absolutely convergent. Okay, doesn't go both ways though, but this is what we're going to use to kind of form our strategy for dealing with absolute convergence. And these questions are really going to jump out at you in the tests and homework because they will ask you to identify whether a series is absolutely convergent, conditionally convergent, or just straight up divergent, meaning that it doesn't converge and it doesn't converge absolutely. So those are the three options on these questions, and you're usually given a choice between those three. Okay, so let's do an example. So I have a series here. It's not all positive, so I can't just say that if it converges, it's absolutely convergent. Okay, so, and you can see the instructions are different. Determine whether the series is absolutely convergent, conditionally convergent, or divergent. So I always start these with absolutely convergent, because if the series is absolutely convergent, that theorem tells me I'm done. I don't have to look any further. So I do start there in the hopes that I get absolutely convergent and I get a shorter problem. The longest is the other two options where I get conditional or divergent. Okay, so we're going to start out by taking the absolute value of the series. Okay, and so really all that does is drop off that alternating piece at the top, and I just get 1 over k to the 2/3. And so this is a p series. And p is 2/3, which is less than 1, which means the series is divergent. Okay, so darn it, it's not absolutely convergent. Okay, but it could still be conditionally convergent, meaning maybe the absolute value didn't converge, but maybe the original series does converge. So that's what we're going to do now is we're going to go back to the original series and we're going to test that and see whether it converges or not. If it doesn't, then the series is divergent. Okay, now looking back at the original series before I took the absolute value, that right there is an alternating series. So I can do the alternating series test on it. So that means I'm going to take the limit of the nth term, leaving off that -1 to the k. And yes, that does go to 0. So the first condition of the alternating series test is met. And then next would be the ratio of successive terms. So I'm going to take ak plus 1 over ak, which looks something like this. 1 over k plus 1 to the 2/3 over 1 over k to the 2/3. And so again, I can flip the bottom one and multiply, and that k to the 2/3 ends up in the numerator of the top fraction. And yes, I can say that the bottom is always going to be bigger than the top here, which means that this is a proper fraction and it's less than 1. So both of the conditions are met. The limit is 0 and the series is decreasing, which means that the series converges by the alternating series test. And since it wasn't absolutely convergent, but it was convergent, we would say that this is conditionally convergent. Okay, so here's a couple more examples for you to try out. So try out the alternating series test and try out absolute convergence on these and see what you get.